All right, as Jason said, I'm Michael Poston from Southwest Research Institute, but today I'll be talking about some work I did on my postdoc with Kevin Hand at JPL. So thinking in terms of RO, the roadmap to ocean worlds, once you've confirmed an ocean, the next thing you want to do is assess its habitability. And a key question there is there exchange between the ocean and the surface? Because exchange increases the odds of chemical disequilibrium, and at least on Earth, life as we know it thrives on chemical disequilibrium. So there was some talk yesterday about trying to get oxidants down through the ice shell. That's one of the big questions there. We can't really look at the ocean just yet, but we are interested in looking at material that comes up from the ocean. And the way to look for that would be to look for the ocean materials on the surface. And if we can find them, how old are they? And that's especially important if you're looking for biosignatures, because we've just been talking about the radiation and how that destroys the microbes and even the amino acids and everything that tells you there was once a microbe there. We also talked about this yesterday, the spectral evidence for chloride-related salts, or at least data consistent with chloride-related salts. So there's the work by Patrick Fisher working with Mike Brown and Kevin Hand, showing the correlation between that third component and the leading hemisphere KS regions, KS being one of the geologic features that could be evidence of material coming up from the ocean. Follow-on work by Fisher in a different wavelength range was also consistent with chloride salts, and work from Ligier et al. Also was interpreted as potentially chloride salts. So the approach we decided to take was to look at NaCl as a tracer of an Earth-like ocean. There's extensive literature in the physics community, starting in the nuclear era, on color centers in sodium chloride, but we didn't find much in the right conditions for Europa. So we ended up going into the lab to do it ourselves. One paper that was mentioned yesterday in the planetary science literature was Nelson and Nash, and they showed in, I think it was 130 Kelvin, that you can get the color center band at 460 nanometers, which is the primary band seen in the physics literature. So identifying such color centers on an ocean world would indicate an exposure of sodium chloride, and we posit that is a good place to look for ocean material. Hand and Carlson went and collected a snapshot of sodium chloride after a relatively large radiation dose, and that's the plot shown here. You can see the relatively flat line that is sodium chloride before it's irradiated towards the top, and then the solid line with all the features in it towards the bottom is after this irradiation dose. But what happens in between? Is it possible that we could actually see how long that sodium chloride has been exposed by looking at the progression from flat line to feature-filled line? I think it was actually in this very room that I drew Carl's attention to this work, this paper, and he went and repeated the work in his lab and presented at LPSC, and also saw the color centers as expected, but he saw extra features compared to what is shown in this plot, a feature at 600 nanometers and a feature at 900 nanometers. So his conditions were pretty different from what Kevin and Bob had done. So that pointed out it may be the exact conditions, exact history may be important. So our science question is, can the dynamics of color center formation in sodium chloride be used to trace the surface exposure age of a sodium chloride deposit, possibly from the ocean, on the surface of Europa? Our apparatus was ultra-high vacuum chamber in Kevin and Bob's lab at JPL. It's with the cryostat running, it's in the mid 10⁻⁹ torr range, so pretty good vacuum. It's about the surface of Europa, if I've heard the numbers right. Helium cryostat for cooling, an electron gun to do the irradiation with. We used the 10 keV that most of Kevin's work is done with, and up to 250 nanoamp per centimeter squared fluxes. We were able to monitor semi-continuously with FTIR, visible near-infrared spectrometer, and a mass spectrometer to see if anything like, say, chlorine came off. We can only talk about vis near our grading spectrometer results today. This table is, I should mention this is all published in JGR, so you don't have to digest this whole table right now, but this is the sequence of experiments that I did, including the places circled in red are irradiation phases, and the gaps in between are watching the decay of the color centers, the annealing of the color centers when we turned off the radiation. Two specific things we tried to do were have 3 different fluxes at the same temperature and 3 different temperatures at the same flux. Relaxation or decay was also done at 3 different temperatures, as well as a sequence of increasing temperatures. And the entire sequence was on the same sodium chloride crystal over a 6-week period without breaking vacuum, except the power failure in the middle. And yeah, so same exact grains of salt. Here I show the initial irradiation, the first, and this is actually divided by the pre-irradiation sodium chloride. That's why we have a perfect line of 1 at the start. It goes from blue to red, and you can see that we formed the features we expected at 460 nanometer and 720 nanometer. We don't see any of those other smaller features in any of my experiments during the irradiation. The 460 nanometer feature is the F center, which is also called the F1. It's a single anion vacancy. So you kick out a chlorine, you get an electron trapped there, and that electron has its own spectra as if it's in a molecule. And that grew in first. The 720 feature was delayed a little bit, looks about a half hour before it showed up. And that is the F2 or M center, and that's 2 associated anion vacancies that are, so two of these single or electrons in a hole basically that are near each other. I skipped over that this radiation was 10 keV electrons, and the dose rate was 5.8 EV per 16 AMU per hour, which for a generic location on mid-latitude Europa is about half a year on Europa's radiation dose. The total radiation shown here is about 200 years. When I turned off the electron gun, I immediately saw feature decay. The primary features decreased in band depth and also shifted to shorter wavelengths, which I still don't understand why that happened. Added some arrows here to draw attention to the 3 extra features. Hibbett saw the one at 600, and I believe Kevin and Bob had seen the 820 nanometer one, and then we also saw the other one that Carl saw, the 930. The 820 and 930 are N centers or F4 centers. They're 4 associated vacancies. And the 600 is in the right region for being F3s, but it doesn't look right compared to the other literature, so I left it unassigned. We also wanted to do numerical analysis to answer our original question. So after playing with a few ways to try and automate the fitting of these peaks, the only thing I could get working with my programming skill was just fixing the edges of the peak and drawing a straight line between those, and then fixing the center of the peak, which works well during the irradiation since the peaks didn't shift until we turned off the flux. So the difference between that line in the middle and the bottom is what I'm using as band depth. And what we have shown here is, these are the trends throughout the course of each irradiation of those 2 parameters. And if the formation of these centers is a competition between irradiation forming them and thermal annealing removing them, then we should get more color centers at colder temperature because the removal of the defects can't compete as well with the formation. And if that's true, the lines on the left should be blue at the top, gold in the middle, and red at the bottom, and that is the case. So we have one line of evidence that it's a competition of thermal annealing versus formation. Here I have the 3 different fluxes all at 100 Kelvin, and the highest flux should form the most defects if things make sense with the previous slide. And if that's true, then the plots on the left should go blue, green, violet from top to bottom. We've got the blue to green part, but the green to violet is within our experimental uncertainty. So we can't draw any conclusions either direction here. It looks promising, but it's not good enough to claim anything. And also during the decay, we saw that the higher the temperature, the faster the decay, which supports a thermal-related annealing process there as well. Finally, trying to get back to our age determination, you may have noticed the plots on the left, they don't really come to the same value at all. So we can't just look at one of the features and say the depth of that feature gives us how, tracking that depth can give us the age of the exposure. But when I took the ratio of the two, they come back to about the same value every time. Again, just barely within the experimental uncertainty. So taking the first irradiation, which would be most representative of a fresh exposure, I was able to fit it with a simple log within a 10% uncertainty again. And it's good out to about 80 EV per 16 AMU, or that's actually about 80 years on Europa, we estimated. So if you just follow if you have a deposit and you see these color centers and take the ratio, if this result is useful on Europa, then you just plug your ratio in as y in that equation, and it tells you the radiation dose that has been experienced by that deposit. And then if you know your arrival rate of radiation from the models we've been talking about for the previous hour, you can back out the surface exposure age. I will go ahead and preempt the question that's going to come. This was pure sodium chloride crystals. This work should be repeated for a brine or hydrates or things that are slightly more, or that are more likely on Europa than a pure sodium chloride. But I'll just go through the conclusions or the whole process again. So the presence of color center defects under irradiation is a dynamic equilibrium of creation and temperature dependent loss. 2 out of 3 tests we did for that supported it. The third was inconclusive. The color centers are created at different rates under different conditions, but by taking the ratio, we found it was largely independent of the factor of 4 difference in conditions we tried. And we actually were able to fit a curve to that and can get an estimate for the surface exposure age at Europa if you know your radiation environment. Thank you.
We've got time for some questions.
So, Roger Clark. First, does the imaging system have bands narrow enough and at locations that it can detect these features? Does anybody know? Anybody on the imaging?
Carl and I were talking about that.
Okay. All right. And then the second question was, what about other wavelengths? Did you measure other wavelengths? Are there any other effects that we can detect? Is there something UVIS or the UVS system can detect, or MISE?
So in the literature that I was looking at 300 Kelvin and at 8 Kelvin, you get this feature right at about 220, 230, shown in the bottom left here. And that's supposed to be stable up to room temperature. So that's a feature. I'm not sure how far how far UVIS goes. Too long? All right. And then the other features that are known in the literature look like they might anneal at too low of a temperature for Europa. But this is definitely something that I'd like to investigate with this work system at SWIRI.
Michael,
On one of the questions we were wondering about these color centers is, do you think that on the time scale of day-night temperature variations on Europa, would you get a change in the intensity? So imagine you're going from 130 degrees down to 90 degrees over a 20-hour time scale. Is that long enough and enough of a temperature change to change those band depths over the course of a day?
All right, so that's a good question. The annealing was pretty fast when I turned off the gun.
So it's not
So you should see.
radiation, it's just changing the temperature with the
Oh, the radiation stays on. You're right. Okay.
What's the difference between 100K and 80K?
So we did 100K and 180K, and we didn't see a big difference in that ratio. So we should be good there. So let's see. The gold is 180K, and the blue is 100K.
Yeah, Michael, nice work. One thing we discussed, you might want to mention, is a role of photo bleaching on this.
Right.
Right.
Yeah.
Bring that one up.
Yeah. So I had the tungsten lamp on continuously for all these experiments, and photo bleaching is definitely something that happens. So even though I turned off the irradiation, I still had this energy source that is known to help these defects anneal faster. There's a lot of cool experiments where they hit with a laser and would preferentially anneal a specific defect.